Welcome to a grand tour of the Carolina Bays. This presentation discusses the elliptical basins along the east coast of the United States called Carolina Bays and those in the Midwest called Nebraska rainwater basins. These elliptical basins form a large semicircle around the Great Lakes that covers many states, but they can be collectively called Carolina Bays because the basins were first noticed in South Carolina. The unusual elliptical geometry of the Carolina Bays was first noticed after the invention of the airplane made it possible to conduct aerial surveys in 1930. The Carolina Bays can be seen in modern aerial and satellite images, but the patchwork of farm fields and vegetation hides many features of the bays. This image uses the LiDAR visualization tool for Google Earth by Michael Davies. LiDAR is a laser ranging technology that makes it possible to visualize small changes in elevation. The topography in this image is represented by a color ramp that repeats every 10 meters of elevation. The centers of the Carolina Bays are relatively flat and they show as a single color that can be easily distinguished from the color of the elevated rims. As we zoom in, the advantages of LiDAR over aerial images become evident in a side-by-side comparison. Many bays have been drained and plowed for farming, while other bays have been kept as lakes for recreational purposes. The LiDAR images show very clearly the overlaps of the bays. The overlaps provide information about the order in which the bays were created. This is a closer view of a community with canals and piers for docking boats by lakeside homes. In 1975, Ayton and Parkhurst pointed out that the Carolina Bays display radial alignment with an apparent focus in southern Ohio or Indiana. This conclusion was based only on analysis of aerial views before LiDAR was available. The Nebraska rainwater basins were discovered in 1994, and their similarity to the Carolina Bays was recognized in 2001. This made it possible to triangulate the convergence point of the bays in Lake Michigan and Saginaw Bay. The glacier ice impact hypothesis, published in 2017, proposes that one or more extraterrestrial impacts on the Laurentide ice sheet by the Great Lakes ejected pieces of ice in ballistic trajectories. The secondary impacts produced seismic vibrations that liquefied unconsolidated soil, and the oblique impacts of glacier ice created inclined conical cavities that became shallow elliptical basins by viscous relaxation. All the Carolina Bays and other impact basins were created within 6 to 9 minutes after the extraterrestrial impact on the ice sheet. The hypothesis that the Carolina Bays originated as inclined conical cavities from oblique impacts is supported by fitting the basins with ellipses by the least squares method and demonstrating that well-preserved Carolina Bays have an elliptical geometry that differs by less than 3% from mathematical ellipses. They are conic sections. The Carolina Bays have often been compared to the oriented thermokarst lakes in Alaska and in other permafrost regions, but lakes formed by ice melt processes do not have the precise mathematical geometry of the Carolina Bays. Using the azimuths calculated from fitting ellipses to the basins by the least squares method provides an objective way of determining the orientation of the basins. This image illustrates the extension of the azimuths of several Nebraska basins and South Carolina bays as great circle trajectories toward the Great Lakes. There is a major convergence point in Wisconsin, which, adjusted for the rotation of the Earth, corresponds to an origin in Lake Michigan. There are also lines pointing toward Saginaw Bay in Michigan. The Carolina Bays and the Nebraska basins are located within 1,500 kilometers from the Great Lakes. This is the range of the ice projectiles in the ejecta curtain produced by the extraterrestrial impact on the Laurentide ice sheet. The sea level has risen by more than 100 meters since the bays were created. Erosion has destroyed all traces of the basins that were made on ground that is now underwater. Carolina Bays only form on unconsolidated soil close to the water table, but they can also form on gravel fields. Carolina Bays are not found on hard ground. Carolina Bays oriented toward the Great Lakes can be found in New York, New Jersey, Maryland, Delaware, Virginia, North Carolina, South Carolina, Georgia, Alabama, Texas, Oklahoma, Kansas, and Nebraska. There are some Carolina Bays in Long Island, New York, but they are not very big. However, these bays are very important because they can be used to determine the approximate time of emplacement of the Carolina Bays. Long Island was created by accumulations of rock debris called moraines deposited by retreating glaciers during the Ice Age. During the last glacial maximum, which has been dated to between 18.7 to 26,000 years ago, the area where Long Island is located was completely covered by the Laurentide ice sheet. The advance of the ice sheet engulfed rocks that were deposited as moraines when the ice sheet melted and retreated. The Ronkonkoma moraine was deposited about 21 to 24,000 years ago, and the Harbor Hill moraine was deposited more recently, about 18,000 years ago. Since the Carolina bays are found on top of these moraines, the bays could not have originated earlier than the last glacial maximum when ice covered this area. The Carolina bays in New Jersey are generally small and seldom exceed 200 meters in diameter. New Jersey has dense concentrations of Carolina bays, but it is virtually impossible to determine the direction from which the impacts were made because all the bays are small, mostly circular, and distorted by terrain movement. This experiment tried to verify if the grape-shot Carolina bays in New Jersey could be produced by a small cluster of impacts by ice pieces on an experimental target. The results confirmed that similar geological landscapes can be produced experimentally. Fitting ellipses to the Carolina bays by the least squares method provides an objective way of determining their orientation. By extending the azimuths of some of the basins in New Jersey, we see that they point in the direction of Hudson Bay. The idea that some Carolina bays are oriented toward the Hudson Bay area was suggested by Richard Firestone in a book published in 2006 and later in a 2009 paper. Firestone's book and his paper were severely criticized by opponents of the Younger Dryas impact hypothesis, but as we can see, some evidence is building up for Hudson Bay as the source of some of the ice boulders that made elliptical basins. This also implies that there may have been more than one extraterrestrial impact on the Laurentide ice sheet associated with the origin of the bays. The Delmarva Peninsula is divided among Delaware, Maryland, and Virginia. The name Delmarva is derived from the names of the states. The entire state of Delaware occupies the northern portion of the peninsula. The eastern shore of Maryland covers the central part of the peninsula, and the southern tip of the peninsula belongs to the eastern shore of Virginia. This LiDAR image around the city of Marydale straddles the Maryland-Delaware border and the northern part of the Delaware Peninsula. This is a flat, sandy, intensively farmed region. The Carolina bays in this area are mostly circular with slightly elevated rims, and most of them have been severely degraded by erosion. The Carolina bays in Virginia have characteristics derived from the terrain on which they are found. We start by comparing the Carolina bays in Machipongo, Virginia with the bays in Windsor, Virginia, which are separated by a distance of only 100 kilometers or 62 miles. Machipongo is in the southern tip of Delmarva and Windsor is further inland. 35 million years ago, a meteorite struck the Chesapeake Bay. For this reason, the ground in Machipongo is very different from the ground in Windsor, Virginia. The meteorite impact created a tsunami that washed away the loose surface sand of the Delmarva Peninsula. The shallow depth of unconsolidated material in Delmarva made it impossible for the secondary impacts of glacier ice to create inclined conical cavities, and this is one of the reasons why the Carolina bays on the southern tip of Delmarva are different from those further inland. The image on the left shows elliptical bays with raised rims in Windsor, Virginia. The bays have been eroded, but the elliptical geometry is clearly defined. The image on the right shows the almost circular bays in Machipongo, Virginia. Although Windsor and Machipongo are separated by only a short distance, the terrain conditions produce different types of Carolina bays. The Carolina bays around Richmond, Virginia are found on gravel and rocky terrain. The Carolina bays in the Midlothian gravels are 15 kilometers west of Richmond. In 1970, Goodwin and Johnson published a guidebook to the geology of the upland gravels near Midlothian, Virginia, and they provided a map showing the Carolina bays in this area. A LiDAR image of the Midlothian gravels shows some Carolina bays in very rough terrain, which is not typical of the flat, unconsolidated terrain where Carolina bays are normally found. These bays could have formed by secondary impacts of ice boulders on a terrain of dry rock debris fluidized by the fluctuating pressures induced by strong vibrations traversing the terrain. Individual rocks that are normally pushed tightly against each other by the pressure of overlying rock debris suddenly become free to slip during a transient low-pressure fluctuation. Strong vibrations from the shock of an impact can briefly fluidize rocky debris and cause it to flow like a liquid. East of Richmond, there are several very large Carolina bays. These are not the typical Carolina bays with level centers. They are on rocky terrain, and the only reason why we know that they are there is because they have clearly defined elliptical rims. These were really huge impacts. Selecting points along the perimeter of a bay and fitting the points with an ellipse by the least squares method provides some really colossal dimensions. The ellipse has a fitting error of 1.7%, which is a very good fit. This ellipse has a major axis of 7,058 meters and a minor axis of 4,699 meters. This Carolina Bay has a length of about 4.4 miles. The glacier ice impact hypothesis proposes that secondary impacts of glacier ice created inclined conical cavities that transformed into shallow elliptical bays by viscous relaxation. The stony ground in Virginia would not have allowed the formation of penetration funnels that those that were made in North Carolina, where the ground was liquefied by the seismic vibrations of the impacts. Instead, the Carolina bays in Virginia were made by ice boulders that disintegrated on impact and plowed gravel and stony debris out of the way to leave the elliptical features that we see today. An experimental impact of an ice projectile hitting a concrete floor shows that the projectile disintegrates into many fast-moving ice shards that can make an elliptical pattern. Assuming that this Carolina Bay was made by the impact of a glacier ice boulder as proposed by the glacier ice impact hypothesis, it had more than enough energy to liquefy saturated soil and to fluidize gravel beds around Richmond. Using geologic equations that correlate crater size to projectile diameter, the ice boulder that made this basin had a diameter of 1,412 meters and a kinetic energy equivalent to 1,700 megatons of TNT. The impact would have generated seismic vibrations of magnitude 9.63. The size of the projectile gives us some information about the thickness of the Laurentide ice sheet, and it may provide a clue about the direction of the extraterrestrial impact. This Carolina Bay near Chester, Virginia has a highly eroded center, but it has a well-defined rim that makes it possible to fit the points with an ellipse. This Carolina Bay has a major axis of 2,682 meters, which is about 1.7 miles. Some of the smaller surrounding Carolina bays have the typical level centers. The fairly flat terrain of North Carolina has many well-preserved Carolina bays. The colorized topography shows a terrain that increases in elevation toward the Piedmont of the Appalachian Mountains very gradually. The Carolina bays have been preserved because the level ground prevents water from running very fast along the surface, and the water percolates through the porous ground and flows toward the sea via underground aquifers. This image shows the amazing elliptical geometry of the Carolina bays near Bowmore, North Carolina. These bays differ from mathematical ellipses by less than 2%. They are truly conic sections. Many of these bays overlap previous bays. Ballistic equations for the flight times of the glacier ice projectiles that make these bays indicate that all the Carolina bays were created within 6 to 9 minutes after the extraterrestrial impact on the Laurentide ice sheet. It was a catastrophic hailstorm. Some Carolina bays have been completely covered by cities. Blythe Bay in Wilmington, North Carolina, has several features that indicate the order in which this landscape formed. Blythe Bay was created first, and then a sand sheet covered the northwest portion of the bay. A few seconds later, a smaller impact made a 1-kilometer bay that neatly clipped the sand sheet. This pattern of sand sheets overlaying bays followed by bays overlaying sand sheets is observed very frequently adjacent to rivers. The sand sheets may have originated from mud splashed by impacts on the rivers that was then driven by the strong winds that accompanied the formation of the bays. In North Carolina, there are many bays close to creeks and rivers that have aeolian sand sheets. These are chevron-shaped sand sheets created by the strong winds that blew during the creation of the bays. The central basin in this image has 3 smaller basins within it that were created by subsequent impacts. When we plot the direction of the sand sheets on a map of the United States, we find that the pattern closely matches the polar jet stream. One explanation for the strong winds at the surface is that the ejecta curtain with the ice boulders in suborbital space flights above the atmosphere trapped the jet stream, which usually is at an altitude of 8 to 12 kilometers, and brought it down to the surface as the ice boulders crashed into the ground. The bays in South Carolina gained wide attention after an aerial survey near Conway, South Carolina, showed a multitude of elliptical basins with raised rims that were uniformly oriented. A 1933 paper published by Professors Melton and Schreiber from the University of Oklahoma wondered whether the Carolina bays were meteorite scars. It did not take long for critics of the impact hypothesis to advance their own explanations, setting off a clash of interpretations that split researchers into 2 camps. A celestial faction favored extraterrestrial impacts, and a terrestrial faction advocated uniformitarian wind and water mechanisms with an aeolian lacustrine hypothesis. Carolina bays are not always elliptical. Some of them became deformed at the time of their emplacement due to the characteristics of the terrain. To understand the geomorphology of the Carolina Bays, it is necessary to be aware of the physical interactions of adjacent and overlapping impacts. This requires awareness of the physical mechanisms of the formation based on experimental physical models that can replicate the features of the bays. The LiDAR image shows a set of overlapping basins. The small basin labeled 1 was in place first, and it was partially overlaid by large basin number 2, and this was overlaid by basin 3. Basin 3 has a pointy shape made by an overhanging flange. This type of structure can be replicated using a physical model to simulate the conditions that form this base. The physical model shows two adjacent impacts. The first one on the right has a well-formed rim to its right. The second one has a stretched flange because the target material did not provide sufficient resistance to constrain the shape. This overhanging flange gives the second basin a pointy shape after viscous relaxation. Viscous relaxation is a geological process that tends to level the ground under the force of gravity. After viscous relaxation, the depth of the cavity is reduced and the high flanges become raised rims. This image shows several bays labeled with the letters A through G in a 4 square kilometer area. We are going to calculate the energy of the impacts required to create these bays. Using the distance of these basins from the Great Lakes in ballistic equations, we calculate that the ice projectiles that made these basins would have had a speed of about 3.2 kilometers per second, which is about 9.6 times the speed of sound. The size of the ice projectiles is calculated from yield equations correlating projectile diameter with crater size. The projectile diameters correspond to about 1/5 the length of the basin. From the volume of the projectile and the density of the ice, we get the mass of the projectile. The kinetic energy in joules is then converted to kilotons of TNT, which is easier to comprehend. The glacier ice bombardment that produced these basins was about 8 megatons per square kilometer. The ecological effects of this tremendous impact energy would have caused an extinction event in the area of the ballistic sedimentation. Before the Younger Dryas cooling event, North America was populated with lions, mammoths, camels, short-faced bears, and other large animals called megafauna. The North American megafauna disappeared at the onset of the Younger Dryas cooling event. A map published by Broughton and Weitzel shows the density of megafauna fossils in the United States. The absence of megafauna fossils in the southeastern United States is notable. South Carolina doesn't seem to have megafauna fossil evidence at all. The impact energy of 8 megatons per square kilometer would have completely obliterated any traces of mastodons and other large animals. We know all this by using the laws of physics as the mathematical foundation for calculating the characteristics of the impact basins and the extraterrestrial impact. The conic sections representing the Carolina Bays and the convergence point by the Great Lakes provide the initial conditions for the physics-based model. The ballistic equations provide the velocities of the ice projectiles. Yield loss correlating impact energy with crater size can be used to calculate the size of the projectiles. These calculations provide information about the extraterrestrial impact. In South Carolina along the Savannah River, there are many impact basins on inclined terrain that have a guitar pick shape. Notice that all the flattened portions of the north side of the bays are at higher elevation than the bays themselves. A downhill impact creates an inclined conical cavity with a steeper grade on the rear part of the penetration funnel. During viscous relaxation, liquefied soil flows into the rear of the basin while the whole hillside slides downward and stretches the basin. Using the experimental model, we can see that the impact of an ice projectile on a viscous target produces a conical cavity that looks elliptical when viewed from above. The downhill impact can be modeled by tilting the impact target in the direction of the impact during viscous relaxation. The rear part of the impact cavity is modified by the flow of viscous medium into the cavity as the whole surface slides downhill. The Carolina Bays deformed on the hills are another example that refutes the Aeolian lacustrine origin of the bays. A large Carolina Bay called Big Bay is located 5 kilometers north of Pinewood, South Carolina. This terrain provides evidence of the high winds on the surface at the time that the Carolina Bays were emplaced. The western part of Big Bay is covered by an extensive sand sheet with many pointy chevrons, and the sand sheet itself is overlaid by well-defined Carolina Bays. The source of the sand sheet was dredged by the wind from the east bank of the Wateree River, which is about 7 kilometers west from Big Bay. The terrain in Georgia is rougher than the terrain in North and South Carolina, so it has fewer impact basins. Water erosion degrades the impact basins very quickly in uneven terrain, and today the Carolina bays are only found on the tops of hills that have a relatively flat surface. Inclined terrain cannot retain the sandy structures of the impact basins. This impact basin is approximately 29 kilometers or 18 miles southwest of Augusta, Georgia, and 186 kilometers or 116 miles from the Atlantic Ocean. The center of the basin has an elevation of 130 meters above sea level. Here is another example of Carolina bays along the Ogeechee River in Georgia. The terrain is rough and the bays are small, irregular, and hard to see even with LiDAR. Alabama does not have many Carolina bays, and even the best ones are not very suitable for determining the headings. Yes, there are Carolina bays in Texas, but not very many, and most of them are not well preserved. A paper published by Richard Firestone in 2009 had an image of an elliptical basin with raised rims in Texas. The scale bar on Firestone's image indicated that the basin had a length of about 2 kilometers. The basins in this image are less than half the size of the one illustrated by Firestone. As far as I know, Oklahoma has only 2 Carolina bays, but one of them is absolutely mesmerizing. The basin is located on the grounds of the Oxley Nature Center in Tulsa, Oklahoma. In 2022, Eric Brown reported an elliptical feature as big as a football stadium that could possibly be a Carolina bay on the grounds of the Oxley Nature Center in Tulsa, Oklahoma. This elliptical basin, which may be a Carolina bay, is oriented toward the Great Lakes. The rim has been neatly sculpted and the adjacent terrain has been modified with tangential lines that align with the equinoxes and solstices. The ellipse itself is aligned toward Saginaw Bay and within the range of other Carolina bays. There is no record of who carved the converging lines or when they were carved. The basin has had many uses during modern times, including as a swimming hole. Several archaeologists have expressed interest in solving the mystery of this solar observatory. It is well known that Nebraska has elliptical basins like the Carolina bays, but this is also true of Kansas. The terrain in Kansas is rough and it has been subjected to a lot of erosion, so it is difficult to see the elliptical basins even with LiDAR. This large basin with a length of 9,423 meters has a basin measuring 1,664 meters within it. The large basin is over 2 kilometers larger than the basin in Richmond, Virginia. The impacts that made these basins were very powerful. These examples of basins within other basins are caused by multiple impacts at the same location by projectiles with different ballistic trajectories. There are some structures near Mineola, Kansas that may be elliptical basins, but they are very degraded. This image shows great circle trajectories for the azimuths of several Kansas basins that were fitted with ellipses by the least squares method. The extensions of the orientations suggest that the ice boulders that made these basins originated from Lake Erie. This is a surprising result that differs from the trajectories calculated for other impact basins. The orientations of the basins in Kansas may be explained by considering that the projectiles that made the basins were diverted by the hurricane-force winds of the polar jet stream. We have seen many examples in the East Coast of strong winds associated with the ballistic sedimentation of the ice ejecta curtain. Adding the vector of the original trajectory to the vector of the wind direction produces a resultant vector whose origin is displaced to the southeast. This means that the projectiles that made the Kansas basins could have originated from the same source as those that formed the Nebraska basins, but the strong wind of the jet stream changed their trajectories. The Nebraska basins are elliptical structures with raised rims oriented toward the Great Lakes. They are analogous to the Carolina bays on the Atlantic Coastal Plain, but they have not received much attention because their similarity was only noted at a conference of the Geological Society of America in 2001. Since then, it has become abundantly clear that the study of the origin of the Carolina bays must include the Nebraska basins. The Nebraska basins have the same mathematically elliptical geometry as the Carolina bays, and their orientations converge by the Great Lakes. Some geologists have proposed that the Nebraska basins originated as deflation basins, which means that they were carved by the wind. But this does not explain the mathematically elliptical geometry and the orientation toward the Great Lakes. The dates of the sediments that underlie the Peoria loess range from 22 to 26,000 years ago, and this is often used by geologists to estimate the date when the Nebraska basins originated. The extensions of the major axes of the Nebraska rainwater basins and the Carolina Bays seem to have several convergence points by the Great Lakes. It will be interesting to see how these intersections develop as new lines are added. Some of the states close to the Great Lakes have a few Carolina Bays. These are a few basins just to the northeast of Grafton, Iowa. Why are there so many Carolina Bays far away from the Great Lakes and so few close to them? This is one of the questions that future researchers will need to answer. Ohio does not seem to have large Carolina Bays. About 4.8 kilometers or 3 miles north of Peebles, Ohio, there are several mesas with very distinctive pockmarks. The tops of these mesas are 267 meters above sea level. The pockmarks in this hilltop are similar to the small basins in New Jersey. The ice boulders that made these indentations had a lot of kinetic energy. The description of the Orleton Farms mastodon shows that it suffered a violent death. The caption of the figure says that the femur has been broken square across. The report says the skeleton proved to be badly disturbed and the bones crushed and broken. As an example of the amount of disturbance, one of the ribs lay beneath one of the tusks, while another was thrust through an aperture in the pelvis. A shoulder blade rested to the right of the skull, and one of the large neck vertebrae was found about 10 feet from the skull, near a portion of the pelvis. In spite of the wide dislocation of the parts, the bones of one of the feet remained intact and in place, very possibly in the spot where the animal last stepped. The Carolina Bays have many mysteries. There are so many things to explore and so many things to explain that researchers with specialties in geomorphology, paleontology, and meteorology will need to work together to find the answers. Unfortunately, at this time, many geologists consider that the Carolina Bays were made by ice melt processes or by wind and water mechanisms, completely ignoring the mathematically elliptical geometry of the bays and the radially convergent alignment. Hopefully, future geologists will be more willing to consider that the Carolina Bays originated from impacts and open new directions for research. If anybody tells you that the Carolina Bays were created by Aeolian mechanisms, challenge them to conduct wind and water experiments to produce overlapping basins with raised rims. Stand your ground. Don't let anybody intimidate you into believing that the Carolina Bays were formed by wind or water without experimental proof. If they cannot produce experimental evidence of overlapping basins created by the wind, remind them politely that a hypothesis that cannot be tested is not a scientific hypothesis. Thank you for joining me in the study of the Carolina Bays. Ask your geology professors to discuss the Carolina Bays because they are the most abundant geological structures in the Atlantic Coastal Plain. There's a link to the LiDAR visualization tool by Michael Davies in the description of the video. My book about the Carolina Bays is available at Amazon. Subscribe to my YouTube channel to be notified of future videos about the Carolina Bays and other scientific topics.